Hind. Myself Pushkal Shukla, Assistant Professor in Computer Science Department at Akgec Engineering College, Ghaziabad. Today I will discuss a theory of logic. This topic is very helpful for the BTech third semester students. Theory of logic. In this topic, we will study what is logical equivalence. So, logical equivalence is one of the feature of the propositional logic. So, already in previous lectures we have discussed propositions or the declarative sentences which is either true or false, but not both simultaneously. So, propositional logic, if we are talking about the propositional logic, so logical equivalence is the important feature of the propositional logic. Two propositions are said to be logically equivalent if and only if the columns in the truth table are identical to each other. Let us take two propositions, say A and B. So, for the logical equivalence, we can write A is logically equivalent to B. In below truth table, we can see we take two propositions A and B, and total number of possible cases will be, since two propositions are there, so 2 to the power 2, that is 4. So, what might be the possible combination, that is true, 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 false, false, true and false, false. So, we have to show that these are the logically equivalent. So, A imply B are identical. So, A imply B and negation of A or B, logical or B is logical equivalence. For this, we have to make a truth table for negation A, that is true, true will be the false, here 2 again false, then false, true and false, true. Then B, this is the B. So, negation A logical R with B is this, true, false, that is true, false, false, that is false, true, true, that true, false and true, that is true. So, this is the negation A logically or with B. This is A implication B. So, two propositions A and B, and we are going to apply a logical operator implication. So, implication जो है, if we will take a operator, so T and T is T, T and false. If first proposition is condition is true and the conclusion is false, then it becomes false. This is A implication B, otherwise it is true. So, true, true, if conclusion and condition both are true, then it will be true. If condition is true and the conclusion is false, then it becomes false, A implication B. If condition is false and conclusion is true, then it is true. And if both are false, condition and conclusion, then it will be true. We see by this example, suppose this is condition part. There is a proposition A, my father will give me a bicycle, and the conclusion part B is I will go to school. So, both conditions are false, means if my father will not give me a bicycle, then I will not go to school. This is logically correct. So, this is true. If I say if my father will give me a bicycle, this is true, and I will go to school, this is logically correct, that is true. If my father will give me a bicycle, then I will not go to school, this is not good. So, this is false, this situation is false. And if my father will not give me a bicycle, then I will go to school, that is true. So, this is A implication B. So, by this, in this column A implication B and negation A or B, TFTT, it means that this column and this column having same truth values. So, we can say that these are the logical equivalent. So, if the two propositions A and B are said to be logically equivalent and it is written as A is logically equivalent to B, if their corresponding truth values of their columns are identical. For example, negation A or B and A implication B is logically equivalent. We see this by making a truth table. The statement negation P and Q and negation P or negation Q are logical equivalents. Since negation P or Q, that is logically equivalent to negation P or negation Q, that is always true. Yeah, we can say by this, yeah, we can combine with the biconditional operators. Biconditional means if and only if, and if we get all the values in their corresponding columns are true, then we can say a logical equivalent. We can see by this, suppose P and Q here two propositions are there. So by making this negation P and Q, and again we have to make a two table for this negation P or Q. Here we can see this and this is same value. So we can conclude that these are the logically equivalent. Yeah, by this implication, this negation P and Q and negation P or negation Q, and logical operator is if and only if biconditional operator, and we make a two table for this, and if we get all the values, truth values are true, then we can say that these are the logically equivalent. So both way we can show it. Next, algebra of propositions. Properties of operators. First, commutative law. Suppose P and Q are two propositions, then P logical operators, that is and Q is Q and P. Yeah, P or Q is equal to Q or P. This is a commutative law where P and Q are the proposition. Associativity. We take three propositions P, Q, R, and P and Q and R. First we perform this P and Q, and then with R, logical and with R is similar to Q logical R. First perform this and then logical AND with P. So we get same value, that is equal, yani ki associativity holds true. Again applicable with logical R. Identity element P logical AND T, T means true, equal to P, and P logical or T is true. Distributive. This is distributive operation, distributive of logical AND with logical R, that is P. We can write here P and Q are P and R. This is logical AND operation with R, and this is logical R operation on with AND this. So distributive law also always holds true. De Morgan's law, very important law, that is negation of P and Q equal to negation of P or negation of Q. Similarly, negation of P or Q equal to negation of P or negation of Q, that is always holds true. Then double negative elements, double negation elimination. So negation of P or negation of P equal to P. This is double negation, that is double negation. Now tautology. Tautology is a statement that is always true. If you make a two table for the propositions, yeah, expressions, and we get the expressions having truth values always true in all cases, then we say it is a tautology. A tautology is statement that is always true. For example, negation of P and Q, by implication negation of P or negation of Q, we see here, we see by this, this is the expression, this is the statement, and corresponding to this the value is true, all the values are true. So, we can say this is a tautology, this is a tautology. If S implication T is a tautology, so we write S is logically equivalent to T, and if S by implication T is a tautology, we write S is logically equivalent with T. Let's see with the examples. Contradiction. A contradiction is a statement that is always false. In case of tautology, tautology is statement that is always true, but a contradiction is a statement that is always false. So, for example, R and negation R, the value corresponding to this is always false. Yeah, negation of P R and Q, by implication negation of P or negation of Q, and this is a tautology, and negation of this becomes a contradiction. So, all the values corresponding to this statement is coming false, therefore, it is a contradiction. The negation of any tautology is a contradiction, and the negation of any contradiction is a tautology. A proposition is satisfiable, satisfiability we are talking. A proposition is satisfiable if its truth table contains true at least once. For example, P R Q. So, if we make a truth table for this T T T F F T and F F correspondingly, P R Q, if we are talking P R Q. So, this is true to true, true false false, false or true, that is false and false. So, a proposition is satisfiable if its truth table contains true at least once. So, here we see that this having at least one true. So, this proposition is said to be satisfiable if its truth table contains at least one true value. A proposition is said to be contingency. A tautology, a proposition is said to be contingency if it has some values true and some value false. Yani neither tautology nor contradiction is known as the contingency. Now, come on the rule of inference. So, inference in AI, we need an intelligent computer which can create a new logic from the old or by evidence. So, generating the conclusion from the evidence and the facts is termed as the inference. Inference rules. Inference rules are the template for generating valid arguments. Inference rules are applied to derive proofs in artificial intelligence, and the proof is sequence of the conclusion that leads to the desired goal. In inference rules, the implication among all the connectives play an important role. Following the some terminology that is used. Implication. See, it is one of the logical connective which can be represented as P implication Q. It is a Boolean expression. Here P and Q are the two propositions. Then the implication, that is P implication Q. This operator is known as implication operator. It means if P then Q. Then converse. The converse of implication, which means the right hand side propositions goes to the left hand side and vice versa. So, if P implication Q, this is a expression. So, converse is Q implication P. So, left becomes right and right becomes left. The converse of this implication is Q imply P. Contrapositive. Now, come on the contrapositive. So, contrapositive, the negation of converse is termed as the contrapositive. So, P implication Q, the converse of this is Q imply P, and the negation of converse is a contrapositive. So, negation of Q imply negation of P is a contrapositive. And next is, this is a contrapositive. This is a converse, and this is a implication. And last one is inverse. If P implication Q is an expression, then the inverse is negation of P imply negation of Q. So, from the above term, some of the compound statements are equivalent to each other, which can prove by this truth table. So, here we see the truth table, we can prove that the P implication Q is equivalent to negation of Q imply negation of P, this one. Here we see TFTT. So, we see here P implication Q is equivalent to negation of Q imply negation of P, and again Q imply P is equivalent to negation of P imply negation Q. So, negation of P imply negation Q, Q imply P, this is implication, and this is the contrapositive. This is again P imply Q is a implication, and negation of Q imply negation P is a contrapositive. So, these are the logical equivalent, and this are logical equivalent. Types of inference rules. So, inference rules basically is rules we can generate a valid sentences based on the premises, based on the evidence, existing arguments. We can create a new sentences by the help of inference rules. So, modus ponens, this is the very important inference rules, is one of the most important rules of inference, and it states that if P and P imply Q is true, then Q will be also true. What it say? If P imply Q and P is true, therefore Q is true. This law is known as modus ponens. P imply Q. For example, there is a proposition P, I am sleepy, P, and Q is I go to bed. There is a two propositions P, I am sleepy, and Q, I go to bed. So, P imply Q, if I am sleepy, then I go to bed. This is true. And statement 2, that is P, I am sleepy, that is P. P is also true. This is P, if I am sleepy, then I go to bed. I am sleepy. Then what we infer, that is Q is also true, I go to bed. So, we infer I go to bed. And modus ponens tells if P imply Q is true and P is true, then we can infer from both statements Q is also true. This is modus ponens. We can see here P imply Q is true and P is true, then Q is true. 1 indicates here true value. Modus tollens. The modus tollens rule states that if P imply Q is true and negation Q is true, P imply Q is true and negation Q is true, both, then it states that negation P is also true. In previous example, if I am sleepy, then I go to bed. This is good. If I am sleepy, then I go to bed. Then I do not go to bed. that is Q, negation Q. I do not, then I am not sleepy, then I am not sleepy. So what modus tollens rules infer, if P imply Q is true and negation Q is true, then negation P will be inferred. Hypothetical syllogism. This rule states that if P imply Q is true and Q implies R is true, then P imply R is true. For example, if P is a proposition, you have my home key, and Q is a proposition, you can unlock my home. You can unlock my home. This P imply Q means if you have my home key, then you can unlock my home. Second, Q imply R, if you can unlock my home, you can unlock my home, you can take my money. What Q imply R is, if you can unlock my home, then you can take my money. So what we will infer from these two? If you have my home key, then you can take my money. P imply R. So this law is known as hypothetical syllogism. Thank you.